Hello everyone, this is our group project. We replicate the paper, Empirical Asset Pricing via Machine Learning. Well, firstly, I will introduce our model. So, for the excess return of stock I in months t plus 1, we have a return Ri t plus 1. And we assume that the expectation of Ri t plus 1 is a function of ZIT. Well, ZIT is a feature vector of stock I at time t. Well, in this model, we assume for all of stock I and all of the time in the same year, they share a same model G. So in this setting, our goal is to estimate this G and evaluate the goodness of this G. The next part is how we divide our samples. So we divide it into 3 parts: the training part, the validation part, and the testing part. We use a special method called recursive method to test our result. And I wish to write it mathematically. It is shown in this picture, and I will show you. The next image will vividly illustrate this process. Okay, let's look at this image. So we have 30 turns. For each turn, the yellow part is the training part. The red points are the validation part, and the last blue point is the test sample. So for each term, we add 1 year in the training part and transfer our validation part to 1 year to give the next to test the next year. By testing in this way, we can make full use of the historical information to assess the standard R-square. And R-square, the out of sample R-square has a formulation like this. This can assess the forecast accuracy. And we also replicated the ranking of variable importance. We rank input covariates by their impact on predictive R-square. For each predictor J, we define its variable importance Vij as the decrease in panel R-square when all values of feature J are set to 0, holding the fitted model fixed. And we call this method zero-out measure.
Next is data construction. Raw sources. We match 3 public available datasets. One is CRSP monthly file, and phone level characteristics, and the 8 Welch-Goyo macro predictors. Then we process the raw data by the following steps. We first filter CRSP to common equities and require non-missing delisting returns. And then we merge the 94 characteristics on permanent number and calendar month. Then we generate macro interaction terms. Finally, we create industry dummies using 2-digit SIC codes.
Okay, let's start with 2 simple linear models. The first is OLS3. It uses only 3 firm trades, the size, book to market, and the 12 months momentum. Because it has few inputs, so it is stable, but may miss extra signals. And the second is for OLS. Here we add all the 923 predicts, including the 860 and 46 micro interactions and 74 industry dummies, plus the same 3 traits. This gives high flexibility but a risk of overfit. And here we check the model scale in 2 ways. The first is the pooled R-squared. You can think we put every stock month into one big pool. It is defined as 1 minus total squared error over total squared return. It's good for testing money value of a strategy. And the second is monthly R-squared. it aligns with the original paper. First, we get 1 R² each month, then average. It's defined as the average of monthly cross-section R². It shows if a model works month by month, not just in total. So why we introduce both these measures? Because the pooled R² tells us trading value, while the monthly R² tells us time stability. So it is fair to use both these methods. And here the table 2 illustrates our results. As you can see, our results are very close to the original paper. Both numbers match the paper within 0.5%. So our data and the code are correct. And now my teammate will show that how trees work to beat these baselines.
This slide shows the result of random forest and gradient boosting regression trees with the Hilbert laws. Well, we select our hyperparameters in the features per split, the number of features per split, the tree depth, and the boosting iterations and the learning rate. And through the testing, validation, training, validation, and the testing process, we can have the out of sample R² for RF is 0.1876%, and the R² for GBRT plus Hilbert laws is 0.09%. These two figures are a little bit smaller than the original paper, but is relatively reasonable for this data. And these three pictures shows how the hyperparameters change through each year. And we also replicate the variable importance process. Because zero out each variable is time consuming, we only perform the zero out evaluation on a shorter subperiod of the data. And this figure shows the zero out importance for features ranked 12 to 11 because the first feature, MV0, dominates. And only 4 of the 10 important predictors coincide with the original paper's ranking, mostly because we only test on a single year. This may have some coincidence.
Next method is PCR. It is a principal component regression. PCR is a two-step dimension reduction procedure. First, principal component analysis condenses predictors into orthogonal linear combinations that maximize explained variance. Second, a subset of leading components is used in a predictive regression. And the number of components k is selected via validation sample. You can see figure 5 for details. The overall out-of-sample R² for PCR is 1.8179%. Next method is PLS, partial least squares. PLS performs a supervised dimension reduction by maximizing predictor response covariance. The number of components k is also selected via a validation sample. See figure 5 for details. The overall out-of-sample R² for PLS is 0.1567%. Next is the variable importance. Figure 6 shows the zero-out importance for features ranked from 2 to 11. The PLS results exhibit high consistency with the original paper's PLS rankings. However, the PCR results reveal notable discrepancies when contrasted with the original paper's PCR rankings. This divergence may potentially be attributable to the limited scope of importance evaluation to a single test year. Thank you.